today we're going to cover some of our recent investments in the UEFI ecosystem. UEFI is a very important technology. It supports many of our products and services, and we engage closely with partners and external communities like Tiano Core and things like the UEFI Forum in order to push initiatives. So I won't have time to jump into everything today in a lot of detail, but I'm hoping to provide an overview, and then throughout the conference, if anything's interesting, you can meet up with either myself or a member of the core UEFI team, and we can talk more about it. Starting with the agenda, we'll start with a quick introduction and then jump into a few different areas covering security, features, we'll look at tests and tools, and then we'll go to some of the things that we're looking at in the future. I doubt we'll have time for questions, but we can meet up at the office hours if there are any questions about this. So I'd like to start by showing how we engage with open source communities and kind of where we sit within Microsoft. The core UEFI team serves kind of like as a bridge between external entities, communities like Tiano Core and the UEFI Forum, and within internal Microsoft organizations. We work in repositories like EDK2 and EDK2 platforms as both contributors and maintainers. We also contribute and maintain and provide a lot of ownership in the PyTool repositories that are listed here. We maintain a project called Project Mu. You can think of that kind of like a fork of EDK2, where we have a subset of packages that we take. We also have some additional code that we keep there that's specific to features that we use within Microsoft products, and we use a different development model there within Project Mu. So primarily we contribute into Project Mu, and then as features mature and they kind of get tested there, we move those features into EDK2. We work closely with various teams and organizations within Microsoft. I've listed some of the ones with ready-to-go logos here, but we do work with others like Hyper-V, and we support Microsoft first-party devices out of Project Mu. Since Project Mu is a key focus area, I just want to show how we have laid it out and like the way that we think about organizing firmware. Starting on the left, we maintain a lot of our documentation, not all, in a repo called Mu. This repo stores the documentation as markdown files. We use MakeDocs to compile that into a GitHub site that hosts our information about the project and different features and philosophy and things like that. Because we break the repos down to a more granular level, as you can see, we consolidate a lot of our infrastructure to maintain these repos in a repository called Mu DevOps. This repository hosts a single place where we have all of our GitHub actions, our things like our Azure pipeline templates, and so a lot of the repos are using the same CI code from Mu DevOps. It supports all of these repos. And it even supports some of our closed source repos as well. We maintain Docker container images there. We use those same images for things like dev containers. So if you go to Mu Tiano Platforms, which is our virtual platform repo, you'll see that you can start very quickly with a dev container that comes from the Docker file that's in Mu DevOps. Mu Crypto Release is where we keep crypto package. We use that to build various flavors of crypto using the kind of dynamically linking approach to crypto, where you have a crypto PPI and protocol. We build various flavors based on various product profiles. Silicon, we keep things like ARM Silicon package in the ARM repo, Intel Silicon package in the Intel repo. Min platform stuff goes in common platform, and then we break things down as features. Inside the core code, core code is code that we don't depend on from core. So core code is kind of like the top of the dependency hierarchy. That keeps Mu base core, Mu Tiano Plus, and Mu Plus. Everything except Mu Plus comes from EDK2. And we started moving some features out from Mu Plus, which is our Microsoft-specific code, into individual feature repos. The idea being that we can put release notes and individual versioning around those repos. It makes it easier for people to understand the changes that are coming, and by following things like semantic versioning, they can see if there's breaks and things like that with the major version being rolled and that type of a thing. These are some of the features we have. Don't have a lot of time to go into all of them. Mu feature config is a way to pass data between various layers of firmware, things like the core, silicon, and platform layers. And it's used in places where DFCI is not really appropriate, so there's not like a strong owner and kind of like managed system model that you would have with DFCI. DFCI is a secure remote solution for configuring UEFI settings. So this is something like zero-touch IT. IPMI is standard intelligent platform management interface server code that we use in server products. The MM supervisor is a supervisor that we run in standalone MM that we published and maintain there. We use this in our Surface products. In the platform side, we maintain x86 virtual platforms and Q35 over there, and a ARM platform through an SBSA package, and then we have sample code that we provide to OEMs in the sample repo. So this is showing that the way that we like to manage code is that we version it, we maintain it with separated boundaries as opposed to a monolithic repo, but then we apply a lot of automation in order to keep those all up to sync. And for example, all of our like licensing files and kind of like GitHub actions are synced from UDevOps to all these repos. So they're always up to date, but they're easier to version and manage when they're integrated into products. Firmware security, I think as Mark mentioned at the beginning of the conference, is a key focus area. This is probably one of the main places we've invested in, not only improving our security, but trying to improve security of the ecosystem. We know that when attackers holistically look at a system, firmware is an attractive target in getting more attention. In particular, operating modes like SML have the ability to affect technologies at the upper layer of the OS stack. So things like virtualization-based security or VBS provide security solutions like kernel isolation, authenticated user credential management. It also provides kernel code integrity, so that ensures that like kernel mode drivers are signed and loaded into proper memory types. Focusing on attack vectors that can affect those types of technologies is a key focus area, and that's why SML is a key focus area. I'm going to go into some of these technologies in this section and the work that we've done. So we noted that if you look at the lower kind of stack of security, a lot of hardware and silicon vendors have put careful attention into building immutable hardware roots of trust that kind of start the overall trusted boot chain. And at the top layer, I mentioned like VBS, and there's many other modern operating system security technologies that have been used to harden the OS layer. Where we found a gap was in the middle. So this is UEFI code itself. And we looked at applying UEFI memory protections more broadly against UEFI code. In doing so, we discovered issues like code dereferencing null pointers, executing code from the stack, running over buffers that would easily be caught with guard pages, and just images that are delivered in binary format that don't have page alignment. So it does not lend itself well to being loaded in memory with things like NX protections. This is an area where we work with partners and we're trying to update the UEFI third-party CA signing requirements, and we, I believe, did in November 2022 to require things like 4K aligned sections. But we're also reaching out to bootloader vendors, shims, option ROM vendors, and commercial third-party EFI applications to fix some of these issues so that we can more broadly enable them across the industry. Taylor from my team is going to have a dedicated talk on memory protections later today, so if you're interested in that, I recommend that you stay for it. Code correctness in this context is mostly referring to static analysis. We know that a lot of vendors run static analysis against the same set of code, and we see the same set of issues, but those fixes don't go back to EDK2. So everyone that's run a basic static analysis tool against the code has probably seen there's no pointers that are not, checked whenever people are dereferencing pointers. There are status codes that are not checked, and you just get thousands of these problems. So one of the areas we tried to do to help here was introduce CodeQL. It's an open source static analysis tool, free for open source projects, into Tiano Core. It works well for distributed working models like EDK2 because it allows you to build a single database, and then you can distribute that database among developers, and you can run queries on it independently to find new issues. So it extracts the relational data from the actual firmware source code and then allows that database to be shared, and people can say, oh, I think there's a new query I want to run to check for dead code or something, right? They can just run that query against the database. They don't have to go figure out how to set up CodeQL. It naturally integrates with things like GitHub code scanning. I'll show an example of that in an upcoming slide. But this is an area that we're looking for collaboration and help from the community in order to understand CodeQL, run CodeQL locally, and try to enable more queries, because more queries we enable, the more powerful it is. UEFI variables are an interesting interface because they're directly exposed to the operating system and they persist data down to the non-volatile layer of firmware. So securing UEFI variables has always been a challenge, and there's been a number of systems and mechanisms developed over time to help do that. A couple of years ago, we introduced UEFI variable policy, which is a way to apply a strong rule set to UEFI variables in order to protect them and to help manage their access all the way through OS runtime. UEFI variables or variable policy is powerful and flexible, so we recommend that if you have not looked at variable policy, you take a look at that and try to apply it to every variable in the system. There really is not a reason a UEFI variable should exist that does not have a policy applied against it. Reducing the MM attack surface, we'll talk about this in an upcoming slide. These are some of the things we'll cover. I won't waste much more time on it here. Secure Boot's an important UEFI security technology. It's one that Microsoft plays a pretty strong role in helping manage. We're coming up to some headwinds in Secure Boot here soon with limited revocation space. So like the DBX variable is up to 89% full with revocations. If you apply all of the architectures that have those hashes in it. Prior to Windows RS 5, we kept all the architectures there, and then we split them out after that. Things like the UEFI third-party signing certificates have 15-year lifetimes, so 2011 certificates are expiring in 2026. These are things that Doug and Jeffrey will be covering later today, so I recommend you stick around for that talk to learn more about the state of Secure Boot and what's happening there. SMM is an operating mode in x86 architecture that is entered by a platform event called an SMI, a System Management Interrupt. It is high priority, non-maskable, and it's broadcast to all CPUs. On receipt of the interrupt, the context of the system is saved in SMRAM, and then the SMM core's job is to go find the proper SMI handler to run in response to that SMI. SMM has been kind of a problem area because it is opaque to operating system software. It's difficult to debug if something goes wrong, if you're not the person who wrote the SMM code or has access to the SMM code. It also requires rendezvous, which affects the performance of the system, especially as the number of cores scales. It's been attractive to people though because of some of its transparent properties. It persists into OS runtime. It doesn't require some of the virtual mode transitions that you have with runtime Dixie code, so you can just continue to use physical addressing throughout SML. It doesn't require special operating system management with drivers, but at the same time, we're trying to take some of that convenience away, or at least provide an alternative for it and reduce the overall surface of SMM code and systems. We'll talk about that. So one of the first things we looked at when containing MM is to enable memory protections. This means taking some of the similar protections that Taylor's going to talk about in his presentation and applying it to MM code. Making sure that there are things like there aren't buffer overflows and people are not dereferencing null pointers and stuff like that. No pointer dereferences sometimes we do see whenever there's like legacy data structures in the first page of memory that sometimes bootloaders are expecting or something, but the idea here is to, if your MM core has the ability to handle memory protections, it'd be considered a medium effort to go through your code and update it in order to work with that. SMM drivers, this of course is just follow best practices. It's kind of surprising some of how many people don't use communicate buffers or don't validate input, have things like nested COM buffer pointers and things like that. In a traditional SMM model, the entire memory map outside of the MM is available prior to SMM ready to lock. And you can get into issues where an SML driver will have valid access to memory outside SML ready to lock to happen, then kind of independently that buffer will be freed, but the SML code still has a pointer to that buffer, right? So one of the things that we've tried to do is lock all of memory outside of SML down from the beginning, and then have explicitly requested buffers be opened up through a library called unblock memory lib that unlocks only buffers that need to be allowed to be accessed by SML. An example would be like the variable runtime buffer and the variable driver. That's like the runtime Dixie buffer that's used between that and the variable SML code. Use standalone ML. I'll talk a bit more about standalone ML, but we think that's important to help prevent some issues like SML callouts. With standalone ML, you get rid of the ping pong back and forth between Dixie code and SML code, and that just helps eliminate a whole host of issues that come up whenever you aren't tracking where your pointers are pointing, and then you call the wrong pointer later in boot, and then you have a CVE filed against you. Finally is enable an ML supervisor. So regardless of the supervisor solution, having privilege separation in ML we think is important. This is containing ML code. So if you have MMI handlers, this is the code that OEMs would provide. Having the ability that if something goes wrong in that code to be able to mediate it is important through a supervisor. There's two models to SML and the PI architecture, traditional and standalone. Traditional is the historical model. This is the model that you're likely using, most products use. You can see the arrows back and forth between the left kind of column and the right column showing the coupling between the Dixie environment and SML. On the right side, we have a lack of arrows. And the nice thing about the standalone ML environment is not only does it help improve security, it also helps improve portability. Once you get rid of all of these linkages back to Dixie code, you can easily take that ML code and move it to something like a PEI launch, which we've done. So in our virtual platform, there is an ability to switch the same standalone ML code between a PEI IPL and a Dixie IPL, and that's possible because the code is not tightly coupled to another PI phase environment. It's very easy to transfer SML code, traditional ML code, to standalone ML. A lot of it involves switching out your entry points, getting a different system table pointer, and changing the module type. But a lot of the code itself mostly stays the same because it's relying on abstractions like memory allocation lib, and memory allocation lib can be swapped out at your build level between going to like a traditional ML library instance and a standalone instance. So in all, we don't think it's too difficult to do the switch here, and it doesn't rely on any differing hardware capabilities. The same hardware can support both models. SML code normally has two phases, one called the initialization phase, one called the runtime phase. This is largely at a spec level. The initialization phase takes place whenever the driver is loaded into memory and dispatched, and the runtime phase takes place after that. As you can see on the traditional ML initialization phase, it has access to many services that are not in the standalone ML initialization phase. And so reducing the ability to even cache pointers or access these services or form dependencies is part of the security value that we see in standalone ML and helping just reduce developer mistakes down the road. In May 2022, we open sourced a ML supervisor I kind of alluded to earlier. We did that because we wanted to make the code available to people to integrate into their platforms relatively easily, but also make it fully available to security researchers. And we have received feedback from security researchers, but we're committed to trying to maintain high levels of security in this code and make it as transparent as possible. So this is what we use in first-party devices that we ship. Platforms can specify an ML policy using an XML file. It has the capabilities to meet Secured Core PC level 30. We have tools that transfer or translate that file into a binary that goes into the firmware and then just gets read during boot. So the final solution looks like a ML that's launched in PEI with an ML supervisor that gets put into the standalone ML environment inside SLRAM. It's enforcing the policy right away, and it helps bring a lot, helps reduce the TCB overall for building up SMM, but it also simplifies its initialization and that everything happens at one point in the boot. You don't have patching and configuration tables and things like that being used. I talked about UEFI variable policy. It's a key mechanism in Tiano Core to secure variables. A variable policy itself consists of constraints that you can place either on an individual variable, such as the variable name and its vendor namespace with, or you can do it on an entire namespace. It's pretty flexible. It allows you to do things like specify the prohibited attributes, the allowed attributes, the minimum size, the maximum size. It also allows you to lock the variable either right away, or you can lock it whenever another variable is created, or you can say, there's a variable coming up I'm going to create and I want to lock it on creation. So it's pretty flexible in the way that you can use it in order to secure UEFI variables. We have the UEFI variable audit test that you can run to ensure that the variable policy engine is running and that it's enforcing policy correctly. There's also a patch series that I have out on the Tiano Core mailing list right now that allows you to dump all of the UEFI variables on a system using a dynamic shell command, and it will tell you the variable policies applied to those variables. So there's ways to both see that the infrastructure is working and that your variables have the proper policy applied. I mentioned that we broke out firmware features into their own area. We did that to try to make them easy to integrate in the products. So if you want to pick up a feature, you don't have to pick up like other feature code that's coupled with it. And I'll talk about some of those here. PRM is it's a way to try to move some of the SMM code out of SMM. So where I talked about SMM alternatives, PRM is an approach to try to do that. And whenever we looked at the number of SMM or the amount of SMM code out there, we had to break it down by software SMM code or software triggered SMI handlers and hardware SMI handlers. And then the even numbers are ones that do not require SMM privilege, and the odd numbers are ones that do. As I mentioned before, some SMM code is there for convenience or just for maintenance reasons, and other code actually depends on hardware segregation of access to system resources because the transaction originates in SML. So in like many platforms, if a transaction originates in SML, it has access to registers and resources that the system does not if it's outside SML. So we broke it down by is SML privilege required or not. There's some examples there of the types of code that's in SML and if it requires the privilege. PRM introduces the capability to move the category 1 and 3, so the odd number ones that don't require SML privilege, out of SML and into a similar environment where they can run without some of the maintenance needed in the operating system, but within the context of the OS or VML. So that kind of takes away their SML privilege that they have, but still allows the functionality to be there. It's common for these types of SMIs to occur from ACPI code, things like a device-specific method or a system event or a device sleep state method may trigger a software SMI to go do something real quick on like the device's way down. So part of the PRM design needed to be able to have a path to take these SMIs that are triggered inside ACPI code from ACPI and move it to PRM. And that's what happened. So this is showing how a PRM or a set of PRM code is invoked. We define two ways to do it. Ideally, drivers would use the direct method. This means using operating system APIs in order to trigger the PRM code. That's just easier to manage at the OS level because we have full visibility into those APIs and stable interfaces that trigger the PRM code. But I also mentioned that ACPI code needs to do it too. And so there's a pathway there in terms of changes that we made to the ACPI specification to add a PRM auth region that can be written to trigger a PRM handler is what the PRM code is called that gets invoked. So looking at the left side, it shows ACPI invocation going from an OS driver through an ACPI method like DSM, hits the PRM op region, and then ends up in the ACPI bridge driver. On the OS driver side, this is direct invocation, so this would be like a driver directly using the PRM interface, but they land in the same spot. And there's a table called the PRM table, PRMT, that's built up during firmware boot from drivers to expose what code is available to be called at the operating system. So those are actually EFI, PE, COF binaries that have an export table, and the PRM functions are exposed in the export table. There's a driver that goes and gathers all those functions, discovers them dynamically through the export table, and then moves them into entries within the PRMT so that it can get called at the OS level. Firmware policy is a way that we've defined kind of like a generic mechanism to be able to share data between different layers of firmware. The idea being there's producers and consumers and consumers go through an abstract interface where data can be produced, and then you can read and be notified on that data. Policies you can think of them as opaque data blocks. They're identified by GUIDs, controlled by attributes, so there's meant to be a level of, or at least a high degree of flexibility there. The policy service itself provides the capability to get, set, and remove policies. You can also unregister them. And there's a concept of verified policies, so this can ensure that things like the data size that the consumer and producer are using are expected, and things like that. I'm going to talk about test and debug tools now. So we've tried to make a lot of the tools that we use for testing and debug available externally, so everything in this section and the entire presentation is open source. I mentioned that we updated the UEFI third-party CA requirements. Have page line sections, ensure that sections don't have like write and execute capabilities combined, and this helps support NX protection. So we use the DLL characteristics bit and the PE COF optional header to be able to detect that. These requirements can be tested by a tool that we have in EDK2 PyTool extensions that is shown here on the slide. We actually use this during our build. We use the DSC and the FDF parsers that are in PyTools to discover pre-built binaries in the FDF, and also discover binaries that we're building, and then ensure that they meet the requirements. So if you kind of want a quick path to be able to see if binaries that you're either receiving or building meet the requirements, that tool's a way to do that. TP on replay is a feature that allows us to replay a custom event log to the operating system. And some operating system features are built around measurements that come from firmware, so PCR 0 through 7. And operating systems, like developers, need to be able to test that either edge cases, what happens if I get measurements or a TCG log that looks a certain way, or you can also reproduce bugs if there was like an issue that you know happened, but you need to reproduce that sequence of measurements. This is a way to be able to create a TCG event log in a JSON or YAML file. It gets compiled into a binary, and then whenever the firmware boots, it actually only makes the measurements that are in this binary to the TPM device, so that you can test those OS features without having to have the OS developers do a lot of extra work. This is useful in places where, like, we use it in QEMU in order to build up a log, and then run an OS test, do a different log, reboot, do another OS test, and it provides that kind of rapid testing capability. I mentioned CodeQL earlier. This is an example of it being used for GitHub code scanning. We have found that it's best to use it with the CodeQL CLI. So there's a command line interface you can run locally. And what we're doing right now is actually updating EDK2 to use the CLI in order to run CodeQL, as opposed to run it in a GitHub action, which is the way that we were doing it before. This ensures that if someone runs CodeQL locally, the results match one-to-one with what they would see in the CI results. And so that's a capability that's coming soon. CodeQL also puts its results out in a file format that's industry standard called Serif, the Static Analysis Results Interchange format. And that allows you to use off-the-shelf tools to view it. And VS Code actually has an extension where you can open up your CodeQL results and just double-click, and it'll take you right to the line of source code that has the problem and tell you what's wrong. So it's very convenient to use. That CLI kind of local developer and CI experience is one that we're going to be bringing to EDK2 here soon. Last topic is future investments. And I'm going to be, it's going to take a little bit of time from our next presentation, but I think that's okay. So we'll just cover these and then we'll jump into the next one. So first is Rust. We've long written firmware in C. Firmware operates in a unique hardware environment that lends itself well to programming languages like C that provide a lot of, I guess, customizability or your just ability to get the language out of your way and do things. Firmware also has very strict performance requirements. We have to meet boot times, both in consumer scenarios and IoT scenarios. It might be the amount of time bringing up a backup camera or loading some type of other subsystem. Developers are comfortable with C that write firmware, and there's a lot of library code written in C. So there's a lot of reasons why it's hard to move away from C. We view Rust as compelling because it provides memory safety with low overhead. I've listed some of the other advantages here. It brings high-level multi-paradigm concepts such as generics and traits, which are useful for developer productivity. It also brings a package management system that we believe is useful. So instead of having to reinvent the wheel on so many of the generic pieces of infrastructure that we use in firmware, we can now take an off-the-shelf crate in order to do that. We've done that for things like page tables and like accessing MSRs and IO ports and stuff already. In terms of our status, we started integrating Rust build support into the EDK2 build environment. We've also started publishing some crates in our Project Mu repos. We have one called Mu Rust HID, where we've published a HID report descriptor parsing stack. And we have this code actually integrated into our virtual platform. So if you're interested in playing around with it, you can go there, and if you build, it'll build Rust code as part of the EDK2 build process. And you'll see a hello world Rust driver run during boot that'll output from the Rust code. We're working on porting more code, so I think this is an area, if you're interested in Rust or collaborating, we'd be interested in working with others on this and trying to figure out how can we make common crates that we can all use everywhere, what makes sense in terms of the crate supply chain and vetting for the safety of crates that we're pulling in from different crate registries, and what abstractions make sense for firmware to use. I think this is my last one. So this is a firmware database is a tool that we've put into EDK2 PyTool library. It allows you to build up a SQL database from EDK2 code. You can generate databases that can be shared. This is different than CodeQL. And you can write parsers that can parse and pull information out in order to help build up that database. There's an example over there showing a VS Code plugin of a database that was built up from an EDK2 workspace. And there's various parsers that we have that are listed here. But this is an area that if this is helpful for you, for your understanding what's in your platform or extracting information about your build, we'd be interested in talking about parsers that make sense and reporting capabilities that make sense here. You can use off-the-shelf tools with it, generic SQL-like tooling. You can also use, we have some report and querying capabilities that are shown here. It allows you to break INFs down by code coverage, recursively show how INFs depend on each other, so you can try to make sense of what's in the firmware code, and then what your platform's using, what code's coming from where. This is an example of code being broken down in an INF, showing test coverage for unit testing around it that comes out from the tool. And this is an example of platform usage, showing for a given platform, where is code coming from? Like where is, I think this was on QEMU, so it's showing where is the libraries and the components that are being built into the firmware actually coming from and how much is coming from those sources. Finally, our virtual platforms is a place where we bring all this together. So if there's a feature that you'd like to test or provide feedback on, or you just want to play around with some of the things I talked about or provide us feedback, you can go to our QEMU Q35 and SBSA packages. They're derived from OVMF, and we try to pull in important changes from OVMF there. But these are the features we have there now. We run our MLM supervisor there. We have PRM integrated. We have the Rust driver running, TPM replays ready to go. And so variable policy is there as well. So all of these things I talked about, you can play around with there if you're interested. And we do provide dev containers, so we try to make it as easy as possible to work out of that. That's all for me. So I'd like to thank you for sticking around, and I'm about 7 minutes over, so I don't think I'll have time for questions, but I'll let Vincent jump into our next presentation.